Okay, good evening, everybody. And welcome to another session of organic chemistry. Okay, today we are going to continue with the chapter 1 that we started on on Tuesday, which is basically dealing with the introduction to organic chemistry. Before we left on Tuesday, pick up my pen here. Okay, before we left on Tuesday, we started with the introduction to organic chemistry, in which we discussed the uniqueness of carbon, and then we started the electronic configuration of carbon and other atoms. So what we are going to do today is simply continue with this chapter 1. Hopefully we will be able to finish this chapter today. And then when we come back on Tuesday, we will begin to do some problems. I also want to warn you that at any time when you come to the class, expect to have a quiz. Okay? Okay, so today we are going to start with electronic configuration. Then we go to valence electrons, discuss valence bond theory, hybridization, and during the course of this session today, we are also going to discuss the various ways of writing organic chemical structures. Okay, starting with electronic configuration. Supposing I ask you to give me the ground state electronic configuration of phosphorus, what are we going to do? Ground state electronic configuration of Okay, what are we going to do? How do we start tackling that problem? Yes. Is that Mitchell? Yes. Okay. You look at the atomic number? Okay. So we have phosphorus. The atomic number is what? Okay, so therefore, what do? We start with the various atomic orbitals, right? What is the first one? 1s2. Okay. 2s2. 2p. Okay. 2p. x2, right? Okay. 2py2. 2pz2, very good. Okay, so far how many electrons have we used? 10. Okay, so we have 5 more to go. Okay, so therefore, keep going. 3s2, okay. 3s2, right? 3 more. 3 more. What do you do with those 3? 3p x 1, right? Good. 1. 3p y1, right? And 3p z1. Okay, and that gives us the ground state electronic configuration of phosphorus. So when you have that kind of problem, the first thing you need to do, of course, you need to know the atomic number. And the atomic number gives you the number of electrons in that atom, right? Okay, and then once you do that, then you simply distribute those electrons within the available atomic orbitals. knowing that you have, you're going to have a maximum of 2 electrons in any given atomic orbital. And then when you have atomic orbitals that have the same energy, if you have to distribute the electrons, you have to ensure that at least each one of those has 1 electron before the other has 2 electrons. So that is why we have 1 here, 1 here, and 1 here. Okay. Now, if you then take a look at this electronic ground state electronic structure, electronic configuration for phosphorus, you look at this here. The last or the outermost electronic shell, which is the 3rd shell. The outermost electronic shell of any atom, we regard that as your valence shell. So this is your valence shell for phosphorus. So if we say that is the valence shell for phosphorus, if I therefore ask you, how many valence electrons does phosphorus have? Those are the electrons in the valence shell. So that is 5, right? Very good, yes. Say that again.
I'm confused with where you found the valence shells other than looking at the periodic table.
Yes, okay. The question is, how do you know which is the valence shell? Is that right? Okay, the answer to that question is the outermost shell that contains electrons. That is your valence. That is your valence shell. Okay. Okay. Now, in that vein, supposing I ask you to give me the ground state electronic configuration of nitrogen. There was somebody who asked us that question last Tuesday. Who was that person? I think somebody asked us to do that last Tuesday. Somebody over there. Okay, anyway. Ground state electronic configuration of nitrogen. Okay, so what do we do? Atomic number? 7. Atomic number is 7. Okay, so what do we have? 1s, 1s, 2, 2s, 2. All of this should be reviewed to all of you. Then 2p x1, right? 2p y1. How many left? 1. Okay. And 2pz1. And that would be the ground state electronic configuration of nitrogen. So in this case, where is the valence shell for nitrogen? Where is the valence shell for nitrogen? The 2nd shell, right? Okay. And that will be the valence shell for nitrogen. So therefore, just a minute. If I ask you how many valence electrons does nitrogen have? 3. It has, you said, oh, I'm sorry. I'm sorry. Let me take that back. I'm very sorry. This here. The outermost shell, which is the 2nd shell. Okay, sorry, take that back. Okay. So how many valence electrons does nitrogen have? 5. 5 valence electrons. Very good. Okay, now let us do the one for oxygen. Oxygen. How many electrons does oxygen have? 8. 8 electrons. Okay. Okay, so we start with what? 1s, 2s, 2p, x, 2, is that right? Okay. 2p, y1. How many more electrons to go? 2pz1, okay. 2p(Z1). Okay, where is the valence shell for oxygen? Second shell, right? It will be this here. So keep in mind the outermost electronic shell that contains electron, that is your valence shell. So that is your valence shell. So therefore, how many valence electrons does oxygen have? How many? 6 valence electrons. Okay. So at this point, I have to take it that each one of you know how to deal with the issue of electronic ground state electronic configuration. So we are going to move forward. Now the question is, why are we interested in the ground state electronic configuration? Why are we interested in the ground state electronic configuration? Anybody has? Yes. To determine bonding? Exactly. In other words, keep in mind, we want to begin to take a look at how these atoms, how they bond to each other. And in order for you to understand bonding, you need to understand the ground state electronic configuration of each one of the atoms. And for the most part, you will find that all of the bonding will take place using the valence electrons. So therefore, it is very important to know about the valence electrons. Okay. So the two questions that we have is, two questions for you. One, why do atoms form bonds? Then the second question is, how do they do it? How do atoms form bonds? Okay, the first question, the answer to that should be fairly simple. Yes, go ahead. Yes, the question.
The first one is somewhat stable.
Yeah, because they want to be stable, right? Very good. Because for the most part, you will find that when these atoms, when they form bonds, the molecule that they form, the new compound they form, they tend to be more stable than the atoms, the individual atoms themselves. So therefore, atoms want to form bonds because they want to be stable. Okay? They want to be stable. Now the question is, the other question is, how do they form the bonds? That's a little bit more complicated. So let us take a look at why do they form bonds. What is the rationale for why they form bonds? To do that, let's go to here. Okay. Why do they form bonds? Now, we have, over the course of the last century or so, made several observations with regard to the chemical reactions of atoms, elements, and the like. If you take a look at your periodic table, this group of atoms here, or elements here, right here, we call this the noble gases, or sometimes we refer to them as inert gases, because they do not react with anything. They tend to be just by themselves. Now, if you therefore take a look at their electronic configuration, with the exception of helium, you will find, well, let us go ahead and write the electronic configuration for neon. Let us do that. Electronic configuration for neon. Take it. Okay, somebody want to help me with that? Electronic configuration for neon, this one here. 1s, 1s2, 2s2, 2px2, right? 2py2, and 2pz2, exactly. Take a look at this. Of course, the valence shell is this one here. How many valence electrons does neon have? 8. Okay, 8 valence electrons. Now, in addition to having 8 valence electrons, what other observation can you make here? What other, yeah, it's stable. Yeah, we know it's stable. What other observation can you make? All of the orbitals are what? They are full. All of these orbitals are completely full. And you could make the same case for argon, for krypton. Each one of these atoms that we call the noble gas elements, if you take a look at their electronic configuration, you'll find that their outermost shell, which is their valence shell, they are all full, and they all have 8 electrons in there. They are all full, and they all have 8 electrons. So therefore, that is the rationale that gives the chemist to think that, yes, in order for a molecule to be stable, the outermost shell must be full. And in this case, they have 8 electrons. And so that leads to the concept of what we call the octet rule. Octet meaning 8. And so what does the octet rule say? Can anybody read for me? What does it say? Yes. Yes.
Elements in the second row of the periodic table need 8 electrons to have no shell of electrons in order to become stable.
Exactly. In other words, elements in the second row of the periodic table need 8 electrons to have filled shell of electrons in order to become more stable. By the way, this also applies to the elements in the other rows. But since most of our time is going to be spent with the elements in the second row, that is why we're paying attention to the second row. So in order for them to be stable, they want to attain a full valence shell in which they have 8 electrons in their valence shell in this particular instance. And to do that, they will want to either lose electrons, gain electron, or share electron. The only exception here is what? The only exception is hydrogen. Okay? Because in the case of hydrogen only has the 1s orbital. And for hydrogen to have a filled orbital valence shell, all it needs is 2. So it simply gains 1 electron. It becomes like helium. So therefore, we have what we call the octet rule. This is a very, very important rule indeed. As we go forward in studying organic chemistry, we are always going to come back to this old concept of the octet. To say, this molecule, is the octet rule, is it obeyed? In other words, does it have 8 electrons surrounding it? Okay, we are always going to be asking you that question. So this is very important. So what do we have here? A filled shell of electron makes atoms stable. We already know that. We also already know that in order for them to have filled shell of electrons, they could either gain, lose, or share. Say for example, let us take for example, go back to here. Let's take for example, if you have sodium, let us say we have sodium. Sodium is in the period 3 right here. Sodium will be okay. And what is the atomic number for sodium? 11, right? Sodium has 11. Okay. So what is the electronic configuration of sodium? Anybody? 1s2, 2s2, 2p, X2, right? 2P Y2, 2P Z2, and then what else? 3S what? 1. What do you think sodium will do in order for sodium to form a bond with another atom? It will lose one electron because it is easier for sodium to lose one electron in order to have the electronic configuration of neon. In order to have the electronic configuration of neon. So in this case, so if we have sodium, we have sodium here. Okay, supposing we also have chlorine. Sodium wants to react with chlorine. What is the electronic configuration of chlorine? Chlorine is atomic number is what? 17. So what we have? 1s2. 1s2, this for chlorine. 2s2. 2px2. S2. 2p y2. 2p z2. Is that right? Is that correct? Okay. Okay. 3s. 3s2. 3p x2. Okay. 3p y2. Is that right? How many electrons so far? 3pz1. Okay, everybody agree? 3pz1. Okay. If you take a look at chlorine, look at the valence shell, which is this here. How many valence electrons does chlorine have? 7. How many electrons does chlorine need in order to obey the octet? 1. So what is going to happen here? If you have chlorine here, okay, you have chlorine. Let's show all of the valence electrons. In the case of sodium, what is the valence electron of sodium? Valence electron of sodium? 1. Okay. So what do you think sodium will do to react with chlorine? Simply transfer this electron to chlorine. And then what do you have? You have chlorine, sodium will now be positively charged, right? Why? Why will it be positively charged? It lost 1 electron. Keep in mind, once it loses 1 electron, you now have you have the proton, which is positively charged. So therefore, you must have 1 positive charge. So therefore, you have sodium. Then what will happen to chlorine? What happens to chlorine? What is the charge on chlorine? Negatively charged because it is receiving an electron. So therefore, you now have chlorine. So these electrons, so it is negatively charged. So your sodium chloride, which is your table salt, what you have in your sodium chloride, which is the table salt that we all eat, it's a combination of sodium ion and chloride and anion. Okay, and in this case, these 2 atoms here, the sodium ion and the chloride anion, they are held together by what we call electrostatic attraction. Take this out. So the sodium ion and the chloride anion are held together by what we call electrostatic attraction. And this kind of bonding is what we refer to as ionic bond. We refer to this as ionic bond. Okay. Well, in this case, sodium has has obeyed the octet rule because it now has in its outermost shell 8 electrons, right? And chlorine also, what has it done? It now has also 8 electrons that has obeyed the octet rule. So for the most part, the driving force for most of these reactions will be attainment of the octet rule. Okay, so that is a very, very important concept indeed. Okay. So we told you now that these atoms want to be stable. In order for them to be stable, they want to form bonds. In order for them to do that, they want to attain the octet condition. So we also told you we have ionic bonding. Ionic bonding. We also have another type of bonding, which we call covalent bonding. Covalent bonding. In order for you to have covalent bonding, let us take a look at the carbon atom. Go back again. In the case of carbon atom, you have carbon, how many valence electrons does carbon have? 4. Okay, the atomic number is 6, but it has 4 valence electrons. So therefore, how many electrons does carbon need in order to obtain the octet? 4. It needs 4. How many electrons does nitrogen need to obtain the octet? 3. Keep in mind, 3. Okay, how many electrons does oxygen need to obtain the octet? 2. You could also, actually, you could tell that by looking at these numbers here. 6. Okay, that means it needs 8. 2 more. 5. It needs 3 to get 8. Look at this here. For carbon, the valence electron is 4. So this tells you the valence electron. Now, if you use the current IUPAC system of designation here, you could then use this instead of 14, just focus on the 4. That gives you the valence electrons. 5, that gives you the valence electrons. For oxygen, instead of 16, it says 6, that gives you the valence electron. So in the case of the halogens, we call this the halogens, which are the fluorine, chlorine, bromine. This group here, the valence electron, 7. You could tell by looking at either you look at this here, that's number 7, or you look at 7 within the 17 number that you are given here. So that gives you the valence electron. So these are very important. Keep in mind valence electron and the octet rule. Now, so in the case of carbon, therefore, what do you think carbon will do? Will carbon want to give off 4 electrons or gain 4 electrons in order to obey the octet? It will want to share because it's much more difficult to give out that much electron or to gain all the way that much electron. So you want to share. And the process of sharing electrons to form a bond is what we call the covalent bond. Okay, so let us go back. So we told you the other type of bonding that you have is covalent bond. Yeah. Now, how do we explain covalent bonding? There are 2 basic theories that we use to explain covalent bonding. 2 theories to explain the first one we call valence bond theory, and the second one we call molecular molecular bond theory. For the valence bond theory, what it's essentially saying is two atomic orbitals overlap to form bonding orbital. It's that simple. So you have two atomic overlaps. Each one of them will have one electron each, and they get close to each other, and then they form a bond overlap. And at that point, the bonding orbital will now be under the control of the two nuclei. That is essentially what the valence bond theory is saying. That's simple. Probably they are so simple that you sometimes wonder, why does it have to become a theory? So this is what we are going to use to explain most of the bonding of interest to us in organic chemistry. Now, just for the record, however, I also want to let you know the other one, which is the molecular bond theory, slightly different. What the molecular bond theory is saying is, if you have, say you have two atomic orbitals, they combine, they mix to form two molecular orbitals. They mix to form two molecular orbitals of different energies. Okay, if you say this is the energy graph, okay, you form molecular orbital with higher energy, another molecular orbital with lower energy. So that is what the molecular orbital theory is telling you. That two atomic orbitals are joined together, they mix together and form two molecular orbitals. And the one with the higher energy, this one here, we say this is an anti-bonding orbital. In other words, it is not used for bonding. And the one with the lower energy, this here, this is the bonding orbital, molecular orbital. Okay, that is all I will say about the molecular bond theory, because it's a lot more complex than what I've just given you. But it suffices to let you know that if you have two atomic orbitals, you form two molecular orbitals. If you have four atomic orbitals, how many molecular orbitals do you form? 4. Okay, if you have 8 atomic orbitals, how many molecular orbitals do you form? 8. That's essentially what that is telling you. And 4 of those 8 will be anti-bonding, and 4 will be bonding. Okay. Okay, now let us now go to molecular orbital, valence bond theory. For the most part, everything we are going to be discussing in terms of this course will be dealing with the valence bond theory. Okay, the valence bond theory essentially tells us that only valence electrons are used in bonding. The valence bond theory tells us that only valence electrons are used in bonding. You now see why it is important for us to focus on valence electrons as opposed to all of the electrons within a given atom. Of course, we also know that we have two major types of bonding. We've told you about the ionic bonding already, so we don't need to tell you more about that. Now the covalent bonding, how does the covalent bonding in valence bond theory, how does it work? You have two atomic orbitals, you have this atom here, you have the orbitals. They simply, the atoms get close to each other, and as they get close to each other, they then form what we call the bonding orbital. Okay, and those electrons within those bonding orbitals will be shared by the two nuclei. And that is what we have here. That's essentially what this is telling you. So if you read that. Okay, so that is that simple. Now, take a look at, for example, let's start with a very, very simple example. Hydrogen. What happens to hydrogen? The hydrogen atom itself, you see two hydrogen atoms. One of them, they only have one valence electron. Both of them come together, and that's what you see here. Come together and then form this molecule here. This now becomes the hydrogen molecule. We could actually measure the amount of energy that is released during the course of this reaction, just to show you that the reason why these atoms want to form bonds because of the stability of the new molecule that is formed. If you take a look at this data here, you have the individual hydrogen atoms right here, the two hydrogen atoms with one electron each to form the hydrogen molecule. This is the energy. Think of this as the energy difference between here. This is the individual hydrogen atoms, another hydrogen atom. They come together to form a bond. The energy difference. In other words, this is the amount of energy that is released. Anytime they form that bond, they release this much energy. So we could actually measure this. And what this is telling us, that the hydrogen molecule is that much less stable, much more stable than the individual hydrogen atoms. And the difference in energy is 436 kilojoules per mole. In other words, once you form that bond, you release that much energy. And whenever you release energy from a system, that means that system is going to be stable. That is what this is telling you. Now, if we want, on the other hand, if we want to break hydrogen molecules into the different atoms, how much energy do we need to do that? How much energy? Exactly. In order for you to break the hydrogen molecule into the individual atoms, you need to give that much energy, which is 436 kilojoules per mole. So this is just simply showing you. This is just an empirical explanation as to why atoms want to form bonds. Okay, so in this case, this is what we call, this is a classic, what I would call a classic covalent bond. Classic covalent bond, in which these two hydrogen atoms here, they are sharing equally you see, they are sharing equally those two electrons between them. Okay, that is complete sharing of electrons, and that is what we call covalent bond. As we move along, you're going to find that there are some variation to that covalent bond system, because it is not all the time that there will be equal sharing of electrons. But this is a very classic case of covalent bonding. Now, let us now take a look at carbon atom. Okay, this is a little bit more complicated. If you look at this, if you take a look at this here, think of this as your methane molecule, right? Carbon is here. So that I could see this. Okay, carbon is right here. Okay, these are hydrogens, right? These are hydrogens. These are hydrogens. You notice what we have here? all of the bonds in this methane, this is a methane molecule, all of these bonds, they have the same length, okay, and also the angle between the hydrogen atoms, this angle here, essentially the same, okay, and that is what you see here. If you look at this, this is your methane molecule right here, okay? This bond here is the same as this bond. The bond length, they are all the same. They are all the same. And if you notice also that, go to the next one, you notice also that this carbon here is in the center of it, what we call a tetrahedron. It's in the center of a tetrahedron. And of course, the bond length here is about 109 picometer. Each one of them, each one of the carbon-hydrogen bonds. And the bond angle is about 109.5 degrees for all of them, this bond angle here. Then the question is, let us remind you of the electronic configuration of carbon. Okay, electronic configuration of carbon is 1s2, right? 2s2, 2p, x1, 2p, y1. So the valence shell is what? The valence shell of carbon is this here, right? Right? And how many valence electrons does it have? 4. Okay, that is good, because it needs, in order for an atom to form a bond, that orbital that it wants to use must contain no more than 1 electron. Okay, so we could make a case that you have all of these orbitals here. Since carbon is going to form 4 bonds, it is going to form a bond with hydrogen. The hydrogen is coming, the 1s electron in hydrogen is coming, and of course bonding with the whatever orbital in carbon. But the question is, if you take a look at this geometry of the electronic configuration, the s orbital, what we say the s orbital is, let us assume that this is carbon here. What is the shape of the s orbital? Okay, we say it is circular, right? Okay, okay. So the s orbital is somewhere here around carbon, right? Now, what is the shape of the p orbital? We have 2 p orbitals that contain electrons. Okay, so let us say the p orbital, you have, let's say we have this p orbital here, right? And then you have, sorry about that, you have the other p orbital, where. Take I use a black pen. Okay, so now you have another p orbital here. Okay, according to what we have here, we have 2 electrons. You want to say that we have 2 electrons right in the, according to what we have here, we have 2 electrons in the s orbital, and then 1 electron here and 1 electron here. Okay, how then do we explain that this methane molecule? Because if you look at this, if we have this s orbital bonding to anything, the bond angle that you're going to see in methane is not going to be 109 degrees. What do you expect the bond angle to be between the bonds? There will be 2 different bonds, right? One bond bonding to the s orbital, the other bond bonding to the p orbital. There will be 2 different bonds in methane, if that is the case. But we only have in methane that we know it's only one type of bond that we have in methane. Okay, and they are all the same length, and the bond angle is the same, 109.5 degrees. So therefore, because ordinarily we would expect the bond angle here between this and this to be about 90 degrees. That's not what we see. So therefore, there must be something else. Before a carbon can bond to anything, something must happen. Something must happen. And that something that must happen is what we call hybridization. Okay, now what is hybridization? Hybridization simply means two things. One, electronic promotion. Two, orbital mixing. Orbital mixing to form what we call hybrid orbitals. Okay? So two things will happen. Electronic promotion, and then the next thing that will happen is orbital mixing. Okay, and that is what we call hybridization. So let us take a look at that. Hybridization. Oh, you want me to go back to the last one? Oh, okay. 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 So, okay. So now let us now explain this process of hybridization. You have, keep in mind now you have in this carbon atom, you have an s orbital that has 2 electrons, right? And the energy level is slightly lower than the p orbital. And then you have the p orbitals. One of them has 1 electron, right? Another p orbital, another 1 electron, and the third p orbital has nothing, right? Has nothing. So what happens here, you have what we call electronic promotion, which means that you have to supply some kind of energy electronic promotion. And that electronic promotion simply means you're going to now promote one of the electrons in the s orbital. Oh, by the way, this is your 2s, and this will be your 2p's. Okay. Okay. So one of the electrons in the 2s orbital will be promoted to here. So what we now have, one electron will now be here, and in the p orbitals, 1 electron is now here. Another p orbital, 1 electron is now here. The third p orbital, 1 electron is now here. Now, at this point, we have done the electronic promotion. Now we are going to now do orbital mixing. Okay, so now you're now going to mix all of the orbitals. Orbital mixing. Okay, some would like putting everything in a bag and just mixing it up, and then you come out with a new shape. Because what are we doing now? We are now mixing. We're now mixing the s orbital. We're mixing this 2s orbital with a 2p x orbital and 2p y orbital and 2p z orbital. And now we're going to end up with what we call 4 hybrid orbitals. And they will look much like this. And they will all now have the same energy. Keep in mind, when we started, the s orbital has less energy than the rest of them. So now your new hybrid orbital will now have the same energy. Now, don't mind my drawing here. I'm not a good artist, so think of this as this here. So now you now have 4 hybrid orbitals. How much time do we have? Okay, we still got plenty of time. Okay, so now you have 4 hybrid orbitals. And each one of those 4 hybrid orbitals contain how many electrons? 1 electron. Okay, let's put the 1 electron in there. Let's say 1 electron here, 1 electron here, 1 electron here, 1 electron here. And each one of these hybrid orbitals was made up with 1 s, a s orbital, and 3 p orbitals, right? So therefore we call these sp3 orbitals. So we therefore call these sp3 orbitals. Each one of those. We no longer call them p, we no longer call them s. They are now what we call hybrid orbitals. Yes. They are mutual, right? Okay.
My question is basically what's on the right hand side is the one as it's the one that's orbital. You just explain it.
Okay.
Wait, are you adding them together?
No, you're mixing them all together.
Oh, can I say adding them?
Huh? No. Don't forget. No. Don't forget what we have here. Let me take this out so that it's confusing. Okay. This is an s orbital, right? Which is the 2s orbital. Okay. Do we agree? This is 2px orbital, right? This is 2py orbital. This is 2pz orbital. Now we're mixing all of those 4 orbitals. We're mixing all of those 4 orbitals, and that is now why we now have what we call sp3. What is sp3 is saying is we have 1 s orbital in the mix and 3 p orbitals in the mix. To do what? Oh no. Forget no. All of these are in these are all in the valence. These are all part of the valence orbitals. Okay. Forget the 2 and all those kind of stuff. Okay. Forget all those. What this is simply saying is, I'll be right with you. What this is saying is we are going to mix these 4 orbitals. We are mixing them. Whether they are in the 2s or the 2p, regardless. We are simply mixing them. Okay, and that mix that we are using, one of them is as an s orbital, and then we have 3p orbitals. 3 p orbitals. Okay, you follow that. And that is why we say we now have hybrid orbitals, and those hybrid orbitals is what we call the sp. This here, we call them sp3. sp3 simply means that we use 4 orbitals to get to these hybrid orbitals. And those 4 orbitals, one of them is an s, and 3 of them is p. That's what that is saying. You follow that? Okay? You follow that? Okay. So now what is now saying, if you now have the carbon atom that has gone through hybridization, you now have a carbon atom that has gone through hybridization. This is what it will now look like. The carbon atom now will now have this. Okay, think of that's the carbon atom, that's the nucleus right here. And then we say it has think of, okay, those are now the sp3 orbitals, okay, around that carbon atom, okay, and those sp3 hybrid orbitals, because they all have the same energy, they all have the same 1 electron each, Okay, and because they also want to be as far away from each other as possible, in order for them to do that, the best angle they can assume will be to have an angle of 109.5 degrees. And that whole concept is, okay, so the bond angle, therefore, here, between this here will be 109.5 degrees. This here, 109.5 degrees. This here, 109.5 degrees. This here, 109.5 degrees. This whole idea of being so far apart from each other, think of it this way. So now you now have this carbon here. Think of this as the orbitals. They are now directed away, as far away from each other as possible. And so we refer to this as the valence shell. Valence shell electron pair repulsion. And the acronym for that is VSEPR. In other words, the reason why we have that bond angle 109.5, because those orbitals want to be as far away from each other as possible. Therefore, the only geometry they could assume is what we call a tetrahedron geometry. So therefore, the bond angle here, the geometry of these orbitals will have to be a tetrahedron. Geometry in which the carbon atom is in the center of that tetrahedron. Okay, yes. They want to be as far away from each other because each one of them contains electrons, and those are negatively charged. They want to repel each other in as much as possible. Okay? Now, yes. Repulsion. Okay, now why do we go to all of this? We're going to all of this to explain how we can get the covalent bond in carbon. In other words, now carbon now wants to bond to 4 hydrogen atoms, okay? Okay, so now you have carbon here, you have 4 hydrogen here, plus a carbon. You want to form methane. You want to form methane, right? So what this carbon will do, it will therefore, before that bonding takes place, it will go through hybridization to form new hybrid orbitals. Okay. In other words, it too simply will not react with hydrogen by using the s orbital or the p orbital. It has to go through hybridization to form the hybrid orbitals before the reaction will take place. So therefore, if you therefore look at this here, look at carbon that is now ready to react with 4 other atoms. Okay? And in this case, the 4 other atoms is hydrogen. Okay, so you have hydrogen here. Hydrogen, of course, we know that it only has the s orbital, right? Which is just spherical. Hydrogen is here. Hydrogen is here. Hydrogen is here. And each one of these hydrogen is ready to undergo covalent bonding with carbon. Okay? And this, of course, each one of these has, you have electron here, 1 electron here. We know that for hydrogen, we have 1 electron here as a result of hybridization and carbon getting ready to react. So now, we have 1 electron here, 1 electron here, 1 electron here. So according to the valence bond theory, they now get close to each other. Okay? And then what do you now get? You now have a situation in which you have this carbon now. Okay, let's say this. Let me use the same blue. Use my blue here. Okay. This here. This here. Those are the hybrid orbitals. Okay. So now we call this carbon here. We call it an sp3 carbon. We call that an sp3 carbon. Yes. Because those orbitals are now hybrid orbitals. They are no longer your regular s or p orbitals. Okay. No, each one of these is an orbital. Each one of these is an sp3 orbital. Okay. So that is why we call this carbon therefore an sp3 carbon. Okay. 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 So now, the sp3 carbon now wants to react with 4 hydrogen atoms. So now what happens now? The 4 hydrogen atoms now come. There's no overlap. Keep in mind, in the case of valence bond theory, there's overlap, right? Overlap. Okay. This is our hydrogen here. Hydrogen here. Hydrogen here. Hydrogen here. So each one of these now is our covalent bond. We have now formed covalent bond between carbon and 4 hydrogen atoms. Okay? And since this is what we call, if you look at this is what we call a head-to-head overlap. Head-to-head overlap. Okay, anytime you have a head-to-head overlap of atomic orbitals to form bonding orbitals, we now refer to that as a sigma bond. Let me write that for you. And I will call that a sigma bond. And we use this Greek symbol, sigma. Okay? So we say this is a sigma bond. So therefore, in methane, if you look at the methane molecule, how many sigma bonds does it have? 4. This is a sigma bond. This is another sigma bond. This is another sigma bond. This is another sigma bond. Okay? And the bond angle between the hydrogen atom is 109.5 degrees. Yes. Yes. Sigma simply means it's a direct overlap. Okay, direct overlap. That's a sigma bond. Okay. So now, that is how we get to explain the geometry. You know, when we say geometry, the spatial orientation of the atoms surrounding carbon. It does not have to be just hydrogen. It could be any other atom that is attached to the carbon. So therefore, anytime you see a carbon atom that is bonded to 4 other atoms, what do you call that carbon atom? sp3 carbon, exactly. So that is the most important information you get out of it. All that, so I've been going through all this, just trying to go through a journey and get into, that is the most important information. Okay. Anytime you see, so therefore, supposing I give you this. Supposing I give you this molecule here. Okay. How many sp3 carbon atoms do we have in this molecule? The molecule that I've just drawn here. How many? 4. Which are the 4? Very good, 4. This is 1, right? This is 1. Okay. Keep in mind, according to the according to the octet rule, carbon needs 4 bonds. Carbon needs 4 bonds, right? In this case, we've shown all of the this is a carbon atom right here. We show all the 4 bonds to hydrogen, to this carbon, to this hydrogen, to this carbon. So about this carbon here, it also has 4 bonds, even though we are not showing the hydrogen. It must have 4 bonds, okay? Because carbon needs 4 electrons in order to get the octet. So those 4 electrons will come from hydrogen. So even though we don't show it, the hydrogens are there. Okay, so therefore, this is an sp3 carbon. Any carbon atom that is attached to 4 other atoms. Keep that in mind, very important. Okay, this is an sp3 carbon. sp3 carbon. This is also an sp3 carbon. Okay, this is also an sp3 carbon. This is also an sp3 carbon. Okay, now, if a carbon atom is only attached to 3 other atoms, okay, let me write it down for you. Carbon attached to 4 atoms equals to sp3. Okay, carbon, take my pen, carbon attached to 3 atoms equals to an sp2. We will tell you why it's an sp2 later. Carbon attached to 2 atoms. What kind of hybridization is that? sp carbon. Okay, so therefore, what type of carbon is this? What type of carbon is this? sp what? sp2. Because this carbon here is only attached to 3 other atoms. Even though it has 4 bonds, do not confuse bonding with the number of atoms that it is attached to. This carbon here is only attached to 4 atoms. Which are the 4 atoms? This carbon here, right? This carbon here, and this hydrogen is only attached to 3 atoms. That goes to the number of bonds that it needs. It needs 4 bonds, okay? But here, in terms of hybridization, in relative to hybridization, it is only attached to 3 other atoms. And anytime the carbon is attached to 3 other atoms, what is the hybridization of that carbon? So therefore, this is an sp2 carbon. About this carbon here, this one here, sp2 exactly. So this carbon also is an sp2 carbon. Okay? Okay, let's give more problem on that. Supposing I have this. Supposing I have this. Okay, I'll go back just a minute. Supposing I have this. Supposing I have that molecule, and I told you to tell me the hybridization of each one of the carbon in this molecule. Let's start from here. This is what? sp3. Very good. See how easy that is? sp3. About this here? sp. About this here? sp. About this here. sp2. About this. 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 And this. sp2. So you are always going to have three types of carbon. sp2, sp, sp2, and sp3 carbon. There are some certain implications to those things that we just told you when we get to chemical reactions. Okay, very, very important. Okay, you have sp carbon. sp carbon will be bonded to how many atoms? sp carbon is bonded to how many atoms? 2. sp2 carbon will be bonded to how many atoms? 3. And sp3 carbon will be bonded to how many atoms? 4. Okay, very good. Okay, so those is going to have those three types of carbon atoms. Okay, now let us see how do we get to the sp2. What time do we have? 8 minutes. Okay, how do we get to sp2? Let me see if I can go to here. Okay, we've done that already. Okay, this is the hybridization for the sp2. Okay, look at what is happening here with the sp2. Here you're starting with, you have a carbon atom that wants to react with 3 other atoms. Because carbon can decide, okay, at this point, I want to react with 3 other atoms. So it will do hybridization that is appropriate to that condition. Okay? So in this case, it wants to react with 3 other atoms. So you have the s orbital, right? A p orbital, another p orbital, another p orbital. Okay, what is it going to do? It needs only 3 hybrid orbitals. Therefore, what will carbon do? Say, well, I don't need this. So it will mix only three of these. So carbon will simply say, yes, okay, all I need is this here, I need these 3. So it will mix only 3 of these. Okay, and which are the 3? One is S, right? And the other is P. The other is another P. It will mix them, and then when it mix them, it now form the. This. This is the sp3. Forget this one here. Let me go to the next one. Sorry about that. Just showing you the bonding that we showed you earlier. Okay. Okay. In this case, we want to explain how a carbon atom you have think of this as carbon, right? Carbon, right? Hydrogen, 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 hydrogen. You notice how flat this molecule is. This is what we call trigonal planar. It's flat. And that is because of the geometry of this carbon. It's an sp2 carbon. Okay, for the sp2 carbon, the bond angle will be about 120 degrees. 120 degrees. And this is what we call trigonal planar. And how do you get to this sp2 hybridization condition? How you do that is, by the way, this molecule is called ethylene. Okay. Okay, this is how it does that. So what it does, it will mix this, okay, to get the sp2 hybridization, what is it mixing? After the electronic promotion, the first thing that happens is electronic promotion, right? Then after that you get orbital mixing, right? Then look at the orbitals that is being mixed here. You have the P, another P, and S. And therefore you now end up with this sp2, sp2, and sp2. And then perpendicular to the sp2 are right here on this plane, and the p orbital that is left. Keep in mind this here, this p orbital did not take part in the mixing, and that is what you have here, right here. And that is perpendicular to the rest of the molecule, to the rest of the orbitals. Yes.
How important are the angles between the three atoms, carbon, are those crucial to know, or is it just?
Yeah, yes, it is. It is important to know. Those angles are important to know. Generally, when you have the geometry of the sp2 carbon, generally the angular relationship is close to 120 degrees. I mean, it's not really. That's all you need to know. It's close to 120 degrees, as opposed to 109 in the sp3. Okay, so it's about 120 degrees because it is what we call a planar molecule. Now, but the important part of this is that p orbital that is left. It's almost as though the p orbital is now up and down. Okay, the p orbital is up and down. We have 3 more minutes. Let me just finish this, and then that will be the end of it. Okay, think of the sp2 carbon. Think of sp2 carbon is here. You have the that's the sp2 carbon with the sp2 hybridized orbital, and then you have the p orbital that is left is right here. Okay, the p orbital is perpendicular to the sp2. So this is p, and this is sp2. This is sp2 right there, the one in blue, and this is sp2. Okay, think of now another carbon atom. Another carbon atom. Now also you have an sp2 carbon atom. This here, and then you have the p orbital is right here, perpendicular to them. Now what will happen? These two now will come together, right? In this case, you have hydrogen is here, hydrogen is here, okay, then hydrogen, let me take this out of the way so we do not confuse. Hydrogen is here, and hydrogen is here. Okay. All of this coming together, what happens when they come together? You now have this carbon with the sp, this other carbon with the sp overlapping. Then you have the other sp with the hydrogen, the other sp with the hydrogen, with the hydrogen. Hydrogen, okay. Okay, just a minute. sp. Okay, just a minute now. Okay. Let me now, no, seriously. So now you now have this. Okay. Okay, so okay, we will continue with this when we come back on Tuesday. Okay. Okay, we will see you guys on Tuesday. So do not forget that you could have a quiz at any time. Yes.
question was that so the p orbitals and the carbons double bond, the p orbitals don't bond. They're just there.
That's what I was going to get. The p orbital will overlap on by the side.
So they're just there.
Well, they're there, but they will overlap on the side. It's almost like you have a sideways overlap.
So it's like a sideways double bond.
Yeah, that's how you get
so
a double bond.
Double bond.
That's double bond.
Thank you.
And that is what you call a pi bond.
Okay.
That's what you call a pi bond. And all of these are the sigma bonds.
I'm glad y'all walked away from the last part with something like, oh, that was like you lost.
Thank you. Okay, so anyway, we'll continue on Tuesday. Okay, yeah.
Can this electron be
Yeah, each one of those orbitals has electrons. This
pi bond could actually jump down that.
To here? Yeah. To here? You mean jump down here? Yeah. No. This whole thing here, this there, that's the p orbital. It's one orbital. So the electron is simply just moving. It's one orbital. Okay.
Here.
Okay. Yeah.
First question is, for your biomedical, you'll take this next semester as well, right?
What's again?